Okay folks, so today's video is on the reactivity series and extraction of metals. Sorry, just move a chair. Right, and as always, we're going to start with a quick quiz. This is stuff that you should hopefully know, but it's important because we're going to be building on it in the lesson. If you find that you can't answer these, are answered in the previous few videos about electrolysis. So if you want to pause the video now and I'll go through the answers in 5 seconds. 4, 3, 2, 1. So what is oxidation? If you remember oil rig. So oxidation is loss of electrons. So oxidation is loss of electrons. What's reduction? Reduction is gain. So reduction is gaining electrons. What do metals need to do to react and become more... That doesn't say stab. Sorry. I was supposed to say stable. Stable. So how can metals become more stable? If you remember, metals are on the left-hand side of the periodic table. So if we pick group 1 as an example, they've all got 1 electron in their outer shell. So they want to lose that electron to become more stable. So the answer here was lose electrons. Remember, metals are losers because they want to lose electrons. And if they lose an electron, they form a positive ion, right? What are positive ions called? Cations. Remember, positive sign, cat ions. So positive ions are cations. And then name an unreactive metal. And we haven't really covered this, but I'm hoping that most of you would be aware, but we're going to build on this today. So I would have accepted copper. So I'm going to write the periodic table symbols, but you can write the words. So we can have copper, silver, or gold, or platinum would have been fine as well. Okay, so moving on. So we're going to look at the reactivity series first. So the reactivity series is essentially a list with the most reactive metal at the top and the least reactive metal at the bottom. But in terms of how we build that reactivity series, so at least initially, so if you would go back a couple of hundred years, and chemists would have been doing experiments to prove this, right? So you take your metal, you put a bit of it with acid and see what happens. Let's make myself a bit more space. So react some of it with acid and make observations. Watch what happens. You react some of it with water and then make observations and see what happens. So I'll just pick a few as an example. So if I pick potassium, I'm going to write down K because that's the symbol for it, but pick potassium. If you stick potassium in acid, it reacts really, really violently, okay? It reacts violently. So, reacts incredibly quickly, very violent reaction. If you stick potassium in water, it doesn't react quite as violently, but it reacts and it forms hydrogen and it makes potassium hydroxide. Right, if I pick another metal, so if I pick gold, right, AU, gold doesn't react with acid, no reaction, and it doesn't react with water. So I know I've already done this as a list, but essentially if you had those two, you can be like, oh, do you know what? Potassium is a lot more reactive than gold because I've seen potassium react with these, it doesn't react with those. So if I then looked at iron, so iron is Fe. So iron, it reacts really, really slowly with water, and it does react with an acid, slowly bubbles away and reacts with an acid. So it's less reactive than, it's definitely more reactive than this one. This didn't react at all, but it didn't react as violently as either of these two. So iron would be more reactive than those, but less reactive than those. Fe. So this is how you build up your reactivity series. And then if I pick calcium as the last one, so Ca for calcium. So calcium, it does react with water to form H2 to form hydrogen gas, and it also reacts to form calcium hydroxide. So that's similar to that one, but with the acid, it does react to make hydrogen. It's just not a violent reaction, so it's less than those. So you use the observations. So you're making observations of experiments, and you can see, based on your observations, you can use them to work out the reactivity series, right? So the more reactive something is, the more reactive it does with acid, put it higher up, less reactive, higher down. So you're literally chucking a chunk of metal in with acid, chucking a chunk of metal in with water, and then comparing your observations. If you think about what's happening, this is why I did these quick quiz questions specifically. So if you think about what's actually happening when a metal reacts, so I'm going to pick sodium as our example. So we've got sodium. It's in group 1, so it's got 1 electron in its outer shell, which means when it reacts, it needs to lose that electron, so it turns into Na+. It's lost the electron over here. So when it's reacted, it's turned to Na+. If you go back to our quick quiz question, so it's lost an electron, it's formed a positive ion, which means it's formed a cation. So what that means is the more reactive a metal is, the more reactive a metal is, the what's the best way of phrasing this? The more reactive a metal is, the more likely it is to form cations. So remember, all metals are losers in terms of they want to lose electrons. If they lose an electron, they're going to form a cation. So if very reactive metals form cations incredibly easily. So the more reactive a metal is, the more likely it is to form a cation. Less reactive metals, so if I pick iron, so Fe, when it reacts, there's a few options here. I'll go with 3+, Fe3+, and 3 electrons here. That does happen, but it doesn't happen anywhere near as easily as this one. So iron is less reactive, so it's less likely to form Fe3+. And then gold is really unreactive, so it's incredibly unlikely to form a cation. Right. So if you look, what actually is this? It's lost an electron, which means it's been oxidized. Now, I know for the last few videos, I've been talking about oxidation being reduction. We've gone oil rig, right? Oxidation is loss, reduction is gain. Now, that when we're talking about oil rig, that is referring just to electrons. There is a simpler way of thinking about this, which is that oxidation equals gaining oxygen, and reduction equals losing oxygen. And that goes against the oil rig. So oil rig is just talking about electrons. But if something's oxidized, it's gained oxygen. So let's talk about this and explain this a bit more. So if you had copper, so if I had some copper and I left it outside for ages, so the copper would react with oxygen. So copper plus oxygen, and it would turn into copper oxide. So you could say, yeah, this copper has been oxidized and turned into copper oxide. That doesn't mean this was wrong, right? If we look at this in terms of the actual chemicals, what's going on here? Well, here we've got copper, which is Cu. It's reacting with oxygen, and it's Cu2 plus and O2 minus. So copper and the oxygen, I know this should technically be O2, and I'll balance it all out. I'm just going to keep it just simple for a second. What's actually happened here, this Cu, it has lost 2 electrons. It has been oxidized. Oxidation is lost. It's lost the electrons because it's given them to the oxygen. And then these two hang around together, right? We don't tend to write it as Cu2 plus and O2 minus. We write it as CuO. We write it as copper oxide. But what's actually happened, it's gained oxygen, but it's gained oxygen because it has lost electrons to oxygen. So oxidation is loss of electrons, which is the same thing as gaining oxygen. Okay, if we did that the other way, so if we had copper oxide and we were splitting it up, so copper oxide, and we're going to do some like electrolysis or reaction on it, we're going to split it up and we're going to turn it into copper and oxygen. What's actually happened here? Well, it's lost, the copper has lost oxygen, so it has been reduced. It's lost the oxygen, so it's been reduced. But if we wanted to talk about it in terms of electrons, remember whenever we're talking about electrons, we go oil rig. What's actually happened? Well, here we had Cu2 plus joined to oxygen 2 minus, and here we've got just Cu. So it's gone from Cu2 plus to Cu. How has it done that? It's gained electrons. Cu2 plus, it's gained electrons, 2e minus, and it's turned back to copper. So this still is true whenever you're talking about electrons. So talking about electrons, oxidation is loss of electrons, reduction is gain. If you're talking in more simpler language, oxidation, something has gained oxygen. Reduction, something has lost oxygen. Right, now let's talk about extraction of metals, which is linked to all of this. Extraction of metals. So you're digging around in Earth's crust, trying to get some metal so that we can, you can use it to make stuff, like a golden throne or something, or get some iron, make a nice iron fence. But we don't dig up iron as pure iron out of the ground. So we dig it out of the ground as something called an ore, and an ore is a compound containing metal ions. So we dig metal out of the ground either as pure metal or as an ore. And if you think, if I buried an iron bar in the ground and then came along, a couple of million years later to dig it up, it wouldn't be an iron bar anymore. It would have reacted. I'd be digging up iron oxide. If I buried a gold bar in the ground, a couple of million years later, it's still a gold bar because it's really unreactive. So the pure metals, we dig them up as pure metals. So gold, silver, platinum, we dig them up and they are totally pure. They are found as uncombined elements. We find them as pure elements in the crust because they are very unreactive. So they haven't reacted with anything over the billions of years the Earth's been around. So we just dig them up as pure elements because they are unreactive. Any metals that are reactive at all, we dig them up as an ore, which is a compound that contains metal ions. And how we get them out of that ore relates to where they are in the reactivity series. So if we have, I'm going to write, so potassium, sodium, you don't have to memorize this reactivity series, right? There's only a couple that you really need to concern yourselves with, but calcium, magnesium, aluminium. This one's important. It's not a metal, but I'm putting it here for a reason. Carbon, and then zinc, iron, copper, silver, and gold. Okay, and at the top we've got the most reactive, and at the bottom we have got the least reactive. So in terms of how we extract these, well, silver and gold, so anything lower than this line, it's not reactive at all, so we dig them up as pure elements. right? Which means anything above the line we dig up as an ore. And how we get them out of their ore depends on whether they are more or less reactive than carbon. There's a reason that I put carbon in here, and that's because what we can do is a displacement reaction. And just to talk you through that, if you displace something, it means you use something if something displaces something, displacement reaction, it means we're using something more reactive to kick out something less reactive. So as an example, we've been mining and we've mined some iron oxide. We're going to react it with carbon because we're going to use the carbon to do the displacement reaction. So if we look here, carbon is more reactive than iron, which means because the carbon is more reactive than iron, it is going to steal the oxygen away. So the carbon steals the oxygen away. So we end up with iron on its own because that's been stolen. So we get iron and carbon dioxide. Okay, so if I was going to write this out, so iron oxide, don't worry about this, you'll get given this one. Iron oxide is Fe2O3, carbon is just a C, iron is Fe, and then carbon dioxide is CO2. I'll just balance this here for a second. Right, so 3 and then 3. Right, so what's happening is these carbons are more reactive than iron, so it steals the oxygen away, leaves the iron by itself. It's a displacement reaction. The carbon has displaced the iron. And if we break down, just going to kind of split this in half and look at what's actually going on. What has happened to the iron oxide? The iron oxide has been reduced. If you remember, if something gets reduced, it loses oxygen. We don't say the iron has been reduced. You're talking about the things over here. The iron oxide has been reduced because it's just been turned to iron. It's lost oxygen. What's happened to carbon? The carbon has been oxidized because it has gained oxygen. And so we've got a reaction here where something's getting reduced and something's getting oxidized. And when those happen in the same reaction, we call it a redox reaction. So a redox is just an abbreviation for reduction, oxidation. So it's a reduction, oxidation reaction. One thing's losing oxygen, one thing's gaining oxygen. So it's a displacement reaction. Hopefully that makes sense. Why can't we do that for aluminium? Well, if we heat up aluminium with carbon, aluminium is more reactive than carbon. So nothing will happen. If we heat up aluminium oxide and carbon, we'd be left with aluminium oxide and carbon. It is not carbon is not reactive enough to do the job with this one. So what we can do for any metals that are less reactive than carbon, we do a displacement reaction by heating them with carbon. For any metals that are more reactive than carbon, that will not work. And for that, so if I pick aluminium as an example, if you've got aluminium oxide and you want to turn it into aluminium, you have to do electrolysis. So it's more expensive because you have to heat it up. You have to heat it up so the aluminium oxide is molten, and then you have to use a whole load of electricity, which obviously also costs money, huge energy bills, and then it splits up the aluminium and the oxygen. Because remember, electrolysis is decomposition of an electrolyte. So when we melt this aluminium oxide, it becomes molten, which means it's an electrolyte, and then electrolysis, we are decomposing, we are breaking it down into aluminium and oxygen. So going back to how we extract metals from the ground, if they're really unreactive, we dig them up as pure elements. If they're more reactive than that, we dig them up as an ore, which is a compound. And then how do we get the metal out of the compound? If it's less reactive than carbon, we do a displacement reaction. If it's more reactive, we use electrolysis. Hopefully that's cleared that up.